Got it? L3, you want to try L3? Because it seems like that might be kind of easy also. L3, all the points look like x coordinate is 0, y coordinate is y, and my y is between what? 0 and root 3 again, but doesn't matter. When I plug in 0, y, doesn't matter. 0 for x, I just get 0. So again, no need to look at a derivative. This is a constant function along that edge. But C1 is going to be a little bit more work. Can I move on? All right, so tell me about C1. What can you tell me about all the points that live on C1? So they all have some x coordinate, right? And then to get the y coordinate, take this equation, turn it into an equality, because if you turn it into equality, that creates the circle, right? The inequality created the shaded part and the boundary, but if we just do equals, it's just the edge. And now solve that for y. And when you solve that for y, you take the root. You're going to get plus or minus, but we're only going to look at the positive root because it's the upper part. So the x coordinate is going to be x. The y coordinate is this solved for y, which is root 3 minus x squared. Does that make sense? Okay, now let's plug that into our function and see what happens. What happens if we replace x with x and y with root 3 minus x squared? Oh, isn't that nice? Look what's going to happen. It's x times this thing squared, which is x times 3 minus x squared. And that turns out to be just 3x minus x cubed. Oh, you know what I did not do? And this I should have put the domain up here. What's our restriction on x here? 0 to root 3. We need that. We have to have a closed interval for this to finish up. So now, what do you mean? We've got a function of x now, right? Now we need the derivative of this. So let's take our derivative. The derivative of this function on that curve C1 is going to be 3 minus 3x squared. And set it to 0. What happens if you set this to 0? You get 3 equals 3x squared. You get x is plus or minus 1. Now, can it be plus or minus 1? No. It can only be the plus 1, right? Because of where we are, right? C has to be between 0 and root 3. So let me kind of restate this. X can only be 1. Can't be the negative. So what is the actual point then? If x is 1, what's the actual point that I have from this? So the critical point is x was 1. What's the y value? You got to plug 1 into this, right? So root 3 minus 1, so root 2. So 1 root 2 is a critical number, and we need to now plug that into the function, don't we? So what is f of this? F of 1 root 2 is 1 times root 2 squared, which is just 2. So we looked, if we step back, we took the partials in the beginning, and we found that, hey, anything along this line is a critical point. We said, all right, we'll move on. We did L1, we said, hey, the function's always 0 there. We went to L3, we said, hey, the function's always 0 there. Then we moved along C1, and we found out that the biggest value that happened was at 1 root 2, and it spit out a value of 2. So now I have to compare everything. What is the maximum value of this function? It's 2. And it happens here at 1 root 2, 2. What is the minimum value of this function? 0, right? Where does it happen? All along L1 and all along L3. So it's difficult for us to just, like, you can't label each point. You could just define, when you write it out, you could write out. But really the book and myself, I'm just going to ask you for the maximum and minimum values. So here you'd say the maximum value is 2, the minimum value is 0. All right, so you see how to handle a circle? You just have to solve the equation. Right, perfect timing for this. And you know what? I don't know if I want to do this problem yet. This problem is not, well, I'm doing this problem up here. I'm going to do it for a reason, but I'm not ready for it. I want to do something out of the book that we're going to be able to get to an answer that's a little bit nice. That'll be the homework. I'll just leave it up there for now. Find max volume of a right cylindrical cone that is inscribed into a sphere of radius capital R. Now, this is actually a problem that you could do in Cal 1. Right? This is a problem that can be done in Calculus 1. I don't know if any of you ever saw it, but it is kind of a classic problem, but it's a little bit more on the more challenging, I guess, side of things. I remember doing this in Cal 1 and hating it. But yeah, all right. So I'm going to try and draw a picture of what's happening here. We want to find the maximum volume of a right cylindrical cone that is inscribed into a sphere that has a fixed radius of r. So if I were to draw a sphere that has a fixed radius of capital R, and I try and fit a cone in here, a right cylindrical cone. So a right cone, we're all familiar with what a right cone looks like? Yeah? Okay, so starting at the North Pole of this sphere, I could have a cone that is very wide and short. That would be an example. Now, when we say inscribed, what do we mean? It's inside, but not just inside, because I could have a tiny little cone sitting in here. It's got to be touching, all right? So the edge of the cone has to be touching the edge of the sphere, and the tip of the cone has to be touching like the North Pole. That's what it means to be inscribed. That blue cone would have some volume to it, wouldn't it? I could also draw a cone that's much taller, right? But if I draw it taller, it's going to hit down here somewhere, right? So it's not going to be as wide. Yeah? Right cone means that if I were to cut it in half, it would look like this. Because you could have a cone, imagine having a circle, and then you could tilt it. You could have a cone that looks like this. Like that. That's not a right cone. Straight up. The radius straight up is to the tip of the cone. All right? So do you see that the blue cone, the red cone, they would give you different volumes, right? So it's saying to find the maximum volume that you could possibly get out of this cone that's stuck in this sphere. The sphere is not allowed to change, but you can change the cone to any shape you want. Now, a lot of people might think, okay, well, what about just halfway? Just go, go to the equator sort of the sphere, and that black cone right there would give you the most volume. Are you sure? Do you know for sure? I mean, maybe your logic's telling you that. So we need to find it with a more precise method. You can't just guess. How in the world are we going to do this? What is this section about? Finding the maximum and minimum values, right, of a function of two variables. So what do we want to find the maximum of? Maximum volume, right? So we need to come up right now with the way to come up with the volume of this cone. So this is the volume of the cone. I'm not going to write this again, but when I'm talking about volume, I'm talking about the cone. What is the volume of this cone? So let's draw an arbitrary cone in here. I'm just going to make up a random cone. This is getting too complicated looking. So let's do something else. How about a real quick picture here? Sphere, arbitrary cone. There we go. All right. What's the volume of that cone? Ooh, what's the volume of any cone? 1/3 base times height times radius square. Where would you find that for me? Somewhere in your book? Google? Your brain? 1/3 pi r squared times height. I think that's what you said, right? Okay. Thought I heard B, but no, you didn't say B. I said because I thought I heard you say B. No, you didn't see B. Okay, that's what I heard. Okay, so the volume of any cone, I'm just going to put this over here. The volume of any cone should be 1/3 pi r squared times height. And what we mean here, just so we understand, the r here, the little r, is the radius of this cone, and the height, of course, is the height of the cone. What's pi r squared times h without the 1/3? That's the volume of a cylinder. So it turns out that a cone is 1/3 of the volume of a cylinder. Kind of interesting. All right, we want to try and get this as big as possible, right? We want to get this as big as possible. Yeah? So let's come back over here. Let me write this down. 1/3 pi r squared h. Could you look at this volume right now as being a function of two variables, r and h? Could you?
Yes.
Yeah, you could, right? You know what? I think because this is our first real example, I think I want to change let's change the radius of the fixed sphere to a number. All right, let's change it to a number. I think doing it arbitrarily might be a little bit too much right now. Let's change it to a nice number too. Let's go 9, because 9 is a perfect square. Is that all right? We'll change it to 9? All right. So we would like to know this volume, the biggest it can be, and here we look at it as a function of two variables. What now? What's 1? What do you mean? I'm not sure what you meant by 1. The volume of the sphere has a radius of 9, right? Yeah?
Would you take the criticals and then restrict the cone from 9 to 9? I mean 3 to 3?
You can take the partials.
Okay, I think we're starting to get there. Yeah, let's try this. You have this function, right, of two variables which graphs a surface. You're trying to find its highest and lowest points, right? Yes? All right. That picture of that surface of that surface V is not here, right? It's not up here. We don't see a picture of it, right? Okay. If I want to know the biggest and smallest this can be, I need to come up with a domain restriction. Are my R and H restricted in any way? This is kind of like the X and Y restrictions. So can you tell me what my restrictions would be? This is the part that gets complicated.
Restricted by H because of the function of the sphere. So
Okay, say that again. You said,
R squared is restricted by H.
okay, so they're connected to each other. What you cannot say at this point is this. You cannot say that the radius must be, R must be between like 0 and 3. You can't say that because, well, you kind of can. If R is 3, if little r is 3, you're right here, aren't you? In the middle? But now your H can only be between here and here, right? But if your R is smaller, right, you could be down here and your H could be taller. So they're connected to one another somehow. It's not as simple as saying, oh, R is here and H is between. What would this distance be from here to here? If the radius is 9. Why did I put 3? The radius is 9, right? This should have been 9. This is 18, right? I need you to understand why this can't be used. This would imply that I could have H is 18 and R is 9, right? Which would mean H is 18 and your radius is 9. You'd be out here, wouldn't you? You'd be out here. No good. Can you come up with some restriction for those variables?
Would you change H into a function of R?
I mean, we need to do something like that, yes? What have we not used at all so far at all in this? The equation of the sphere. Can we jot that down real quick? Let's just jot it down. What's the equation of this sphere? X squared plus y squared plus z squared equals r squared, which is 81, right? So we have that. So any point that lies on that sphere, right? Any point that lies on that sphere must satisfy this equation. So let's take some arbitrary point on this cone. What can you tell me about that?
H is 0.
H is 0. Where is H on this? H is the distance from the North Pole to right there, right? So what is H there?
H is 0.
I mean, do we know? I mean, it's just H, yes? What is the R? It's this distance here, right? Do y'all remember this at all from Cal 1, seeing something like this, like what to do? No? Yes? You have an idea?
Well, in Cal 1 we would use the volume of the sphere. So we would plug it in and then we would find one of the variables in terms of the other. Like,
Yes. Okay. In Cal 1, here's what we do. Maybe it'd be good to remind you what we do in Cal 1. In Cal 1, what we would do is we would take this sphere, and let's just, I want to just almost start over, okay? Just because I want you to see it from the Cal 1 perspective first and see, you've got to find some value in what we're doing now. And I think the way to find value in what we're doing now is to understand how we did in Cal 1 first. Okay, in Cal 1, we would have this sphere, it has a radius of 9, and we have this cone inside of it, all right? There we go. So what we do is imagine cutting this in half and looking at it. And what you'd have is a cross section. You would have a circle, and then you would have this cone. And the cone would be in here like this. And then what you could imagine is just looking at, this is the center of the sphere, right? What you could imagine is that this piece right here is what? Little r, right? That's the radius of your cone. And then this from here to here is what? H. And then is there anything else that you know?
Yeah, you can figure out what the height.
You know that this piece right here is what? Big R, which in this problem would be 9, right? And what is this piece right here? What's from here to here? Which is what? 9. And then from here to here is H. So this should be H minus 9. Right? And what do you have now? That little thing I drew here. A right triangle. And so you have this relationship that this side squared plus this side squared is this side squared. H minus 9 squared plus R, plus R squared equals 81. And what we've created is a relationship between R and H. So when we want to figure out what the volume is, if we want the volume, we know it's 1/3 pi r squared h. What we need to do in Cal 1 is eliminate one of these variables. So we come over to this formula and check it out. If we solve this for r squared, what do we have? 81 minus h minus 9 squared. If we take 81 minus h minus 9 squared and replace this r squared with it, 81 minus h minus 9 squared, that's replacing the r squared times h. Now we have a function of a single variable. And once you have a function of a single variable, you can do all your calculus that you did in Cal 1. Do we have a closed interval? Do we have a restriction on the variable h? What is the smallest h can be? Smallest. 0, and the biggest h would be all the way down here, which would give you a 0 radius, but you would be looking on the closed interval 0, 18. And that's how we did it. We take the derivative of that, set it equal to 0, figure out where it's undefined, and work through it. All right? Does that at all look familiar? Maybe, maybe not. But this is a different section. This is Cal 3, and we are able to find maximums and minimums of functions of two variables. Right? We are. The function we have is this right here. What we don't have is the restriction. What is the relationship between the R and H? So let's see if we can't come up with it. Still don't, I don't think y'all are seeing this. Huh? It does. I mean, we could do the same picture, couldn't we? We could do the same picture. Yeah, we can talk about that relationship, but what is that relationship?
Would r squared be x squared plus y squared plus z squared, and then h would be like the height?
R squared would be
X squared plus y squared plus z squared. Since the radius is 9, r squared is 81. And
81, yes. I'm not sure what you're saying. This equation here,
Yeah, replace
then,
it.
yeah,
but replace what?
with r squared on the volume of the cone.
Oh, with this. Oh, but this is the radius of the cone, not the sphere, right? That's the difference here. This, so we've got this sphere, right? And this cone touches the edge. You're trying to come up with some way to restrict H and R so that you can find the max of that or min of that, right? All right, let's do this. Let's act like there's no restriction, okay? Let's just act like there's no restriction. What would our procedure be for finding the max and min of this? What would our procedure be? Find the partials, okay? So let's take the derivative of this with respect to what? R little r first, and what would we get?
1/3 pi 2r h.
So I'm going to put 2/3 pi r h, right? That's what I would get? Okay, then I take the partial with respect to h,
Which is 1/3 pi r squared.
which is 1/3 pi r squared. And now I have to set them both equal to 0, right? So what will we get if we set this one equal to 0?
H is equal to 0.
Equals 0 means that
H is equal to 0 or r
h is equal to 0 or r is equal to 0. Okay, and then this one's set equal to 0.
r is equal to 0.
R is equal to 0. But if r is 0, then what? If this says r is 0, so if r is 0, what can h be? H is free. That's bad. That's like an entire line again that we have, if you're thinking of it in terms of like x and y. Now, what about the other possibility? We could have r being 0 and h being 0, right? But what would our volume be at that point? 0. So what I'm getting at is that if you don't restrict the domain, you're never going to get an answer because it's either going to be 0 volume or basically an infinite volume.
So could you restrict the BH?
Can you do what?
Would the domain BH from the max to, so H would be between 0 and 18 because you can't go past the 2R for H.
What? Guess what? Imagine the cone. See, this is not working. Imagine the cone looking from the top down. Okay, look at the sphere and look from the top down, and imagine you're up at the North Pole, and then you start drawing the cone down. It's gonna do what? What you're gonna have like a little circle that's and it's gonna get bigger. When it gets to the equator, it's going to get smaller, right? Back down to a point. And that thing that's happening, the relationship is again between the h and the r, the radius of the cone.
So,
What if, how come you can't restrict just R? Because it's.
If you restrict just r, what are you going to restrict it to?
The radius, to R, to 0 to 9.
Less than x, less than or greater to x, which is less than greater to
You want r to be restricted where?
From 0 to 9?
0 to 9? Yeah, but then you have to put a restriction on x, though. I mean, on h.
On H?
See, this is what I was saying earlier. You can't do this restriction. You can't go from 0 to 18 because then you have a point that's outside of the sphere.
so, and before we would say it's 0 between x squared plus y squared and then 9. You can say the same thing for r squared between 0 and 9. So wouldn't you say r is equal to x squared plus y squared?
Say it again. I'll try to write it down. We'll look at it. Say it again.
So, if you're looking from the top down, you would say x squared plus y. 0 is less than or equal to x squared plus y squared. And less than 9. And you could say the same thing about the radius.
I thought that was the radius. No?
Yes. So then you would say that squared, the radius equal to x squared plus y squared.
This is r squared now?
Oh,
What is it, R squared plus A squared?
make
Yeah.
that into.
Where, I think y'all are seeing, man, you know, I probably should have started without a cylinder. I should have gone with the, the right cylindrical cone. I should have done just a right cylinder to start, because it's an easier domain to mess with.
Like, if you make a triangle, pretty soon you look down and like, it goes out and then like in. So like
Mhm.
that outer, like the outer line right there would create like a rectangle.
Mm-hmm.
And then the short length or whatever would be like the R, and then the H.
I think you're talking about this. I don't know. Is that what you were doing?
Yeah. And then wouldn't,
And then the center of the sphere is somewhere in here. It doesn't have to be at that right angle, something like that. This is looking a lot like the last picture, though.
well,
I don't know if that's what you were saying.
because you're saying like, if you look at it straight down, it like goes out, and then once it hits the outer, it goes back in.
Mm-hmm.
So then wouldn't the center be at the right, the point down? Yeah. Wouldn't that be where? You know what I mean? Because wouldn't that be at the center? You said it goes out and then it goes back in.
Yeah, this is your circle down here. That would be your center.
Yeah. So I don't know. Never mind.
Yeah. I think some of you are on the right track, but I'm having trouble understanding how you want me to write this up here. We can do it with Cal 1. That's not the point. The point is to try and do it with the restriction on R and H and do the technique that we were just doing. Let's do this. I was afraid to go out a little too far. Let's try something a little bit easier, because we still have enough time to do something. Let's do one easier, and then I'll give you time to think about this one and see if you can do it with the two variables. Let's do something a little bit. There's one in the homework that I ask you to do that's like this. So, do you? That's the question. Do you? If we write one in terms of the other one, we're back to Cal 1, right? Because then we get everything in terms of one variable, and then we can do it using Cal 1. Question is, can you do it with this?
What we would write in terms of kind of because if you look down, then you get almost like a function of cosine squared or cosine of x, y.
I want you all to think about it, okay? Because I want something to come out of this last 20 minutes rather than what's happened. So let me, all right, let's do this one. Find 3 positive numbers. This might shed light on what we need to do on that last problem. 3 positive numbers whose sum is 100 and whose product is a maximal. All right, so this question is not geometric at all. It's a ridiculous question that we probably would never need to do, but it helps us get the ideas of setting these things up a little better. All right, you have to find 3 numbers that are all positive numbers, okay, that add up to be 100. But when you multiply these 3 numbers, you need to get the biggest number possible. So if anyone else gave me 3 other numbers that added up to be 100, their product would be less than mine. Make sense? Okay, so let's just write some things down. We have 3 things we don't know, right? We have x, y, and z. 3 numbers that we have no idea what they are. Here are some things we know about it, though. We know that they add up to be 100, right? What is it that we want to find the maximum of? Find the maximum of the product, right? So we'll call it P. And what is the product? x, y, z. Okay, how many variables do we have there? 3. I can't do the maximum and minimum of 3 variables yet. It's coming, all right? It's coming. 11.8 is, we're going to have an easy way of doing all these problems. Easier than this, for sure, all right? So for this, I could do a product function. I could find the maximum. If it was just a function of 2 variables, I could do it, right? So, but can you make this a function of 2 variables? So I can solve any of these for, right? I can use that equation because this has to hold, doesn't it?
Yes.
So why don't I solve that for z? I'll have xy times what's z? 100 minus x minus y, right? And then you could distribute through. You get 100xy minus x squared y minus xy squared. So there is a function of 2 variables, right? There is a function of 2 variables. 100xy, x minus x squared y minus xy squared. Yes? Okay. This whole section is about trying to find the maximum and minimum of these of a function of 2 variables. Do I have some sort of restriction on x and y? X plus y has to be less than 100. Let's write some things we for sure know. X has to be bigger than or equal to 0. Y has to be bigger than or equal to 0. Oh, no, they said positive, right?
Yes.
Sorry, they have to be strictly greater than 0. I know that because they're positive numbers. What is the absolute maximum that x could be? They have to add up to be 100, right?
98.
They're not, it doesn't say integers. So, you could have, you think you could do like 99.9 and then these 2 or 2 others and it adds up to be 100? Yes? So, x has to be between 0 and 100. So we're going to run into the same issue here. What about y? Can you say 0 to 100? Why can't you say 0 to 100? Because what if x is 100? What if x is 80 at the same time y is 80? See, when you draw your region, you're trying to figure out what your x and y's have to be, right? So look, here's 100, here's x, here's y, right? We know that if x is 100, y's got to be very small, right? And if x is very small, y's got to be very big. So there's probably, like, if x is 50, we could have y be 50, or right? That would work. And z would have to be 0. So maybe there's some relationship between the two.
Like, if y was 100, x would be 0, and y is 0, x would be 100.
So like 100 here,
And just a line
like this.
Yeah, then we're going to go and look at
And then what did
each
you
side
find?
of the line, like we were doing with the problems
And
before,
what did
right?
you find this slope?
Like L1, L2, L3.
Something like that. Now, to draw this picture, we would be assuming that what?
Z is 0.
Z is 0. But can we assume that? I mean, if z is 0, z can't be 0, can it? No. So is this a closed bounded region? No? Okay. I think we have a lot to talk about next class. I think we do. Was this setup of this one a little bit more straightforward?
Would
3 numbers that add up to be 100, Their product has to be a maximum. We set up the product. We replace one of the variables. Now it's the restriction part that we're...
Would you do the same thing with R and H?
You have to do the same sort of thing with R and H, yes. But it's not... This one is cleaner, but it's still not as clean. It's not super clean. I want you all to think about it. We're going to come back. We're going to have to finish this section up. Right now, you can do 3 through 13, 23 through 27. 37 is a word problem like this.
Would it be almost like a partial derivative chain rule problem? Because,
How do you mean?